So Kepler was a German mathematician, astronomer, and an astrologer, as I told you. He was actually working on a project where he was observing the planetary motions of the planets and with respect to the sun, and he formulated three laws. First law stating that the orbit is of a planet is elliptical in shape. Second thing, he said that the satellite or sorry, the planet sweeps equal distance or equal area of the orbital plane in equal amount of time. So that also meant that if so first is, yes, the first law I said is an ellipse, and one more point I forgot to tell is an ellipse have two foci and your mass center. What is the mass center? Mass center is for a two body system, where the mass of the two body will lie, that will be lying at the foci. And since earth is very sun is much heavier than the planet, the barycenter lies at the sun, and sun is at the one of the foci of the orbit that we are talking about. And then comes the second law, which states that the equal area. So we could see that A1 and A2, since the distance of the planet at this particular point at A1 is less as compared to this, the width covered by the planet will be more, or a distance covered by a planet will be more when it is near to the sun as compared to the point which is at, say, apogee of an orbit. So that also proved that the velocity of a planet will be higher when it is near to the mass center and low when it is away from the mass center. This is also because it has to balance the gravitational pull to maintain its orbit. Then next, third law, we were at the third law, we covered this much. We also proved the velocity. Yes, this I had already shown you, and I had shown you that the 10-day period, as you can see, that day 0 to day 1, and how this the distance covered is changing. And this also meant that at apogee you will have a larger time to actually communicate compared to when you are near to the perigee, or basically a larger sight time, we call it as. The satellite will have a sight time, or an earth station will have a larger sight time for the satellite, because it is moving very slow. Now coming to the third law, we have started with the third law, so I'll just use the whiteboard for this particular okay. So the third law states that the third law states that your square of the time period is proportional to the cube of the semi-major axis. Now semi-major axis is nothing but it is also the basically 50% of your the line of abscissa. Now how do we prove this? Is your time is equivalent to, if I'm taking an example of a circular orbit, it time taken to cover is divided by the velocity. Now, what is your velocity? The velocity is equivalent to r to power of 1 by 2. This is the law that where mu is your gravitational constant. Okay. Now, what we have to do is just substituting it here. What do we get is, let me stop share. An advantage of finding the velocity. Now, how do we calculate the velocity? Now, how do we calculate the velocity? Let's take an example of a circular orbit. Now, circular orbit, you know that the velocity is nothing but speed is equivalent to distance upon time. So, let's say I want to calculate the velocity. Velocity is equivalent to distance upon time. So for circular orbit, how much will be the velocity? What is the distance that the satellite is traveling? So it is 2 pi into r divided by the time is 24 hours, which is equivalent to 24 into 60 into 60. Correct? Now, can you calculate and tell me what will be the velocity of the satellite in a geostationary orbit? Now, suppose this is a center and this is a circular orbit. Now, what is the radius? Radius will be from the center? Yes or no? Okay. So, this radius will be nothing but R will be equivalent to the height, which is 36,000 kilometer from the surface of the earth, plus the radius of the earth. I'm really sorry I missed this point, and therefore that needs to be used for calculating your velocity and your time period. 36 or 642 400 3.08. Yes, perfect. Crucial. The time is also coming perfect. That is 23 hours, 79 minutes. So the mistake, now we know what we were doing was, I was just taking r to be the height from the surface of the earth, which was wrong. The actual radius is right from the center of the earth, which is equivalent to 42,000, around 42,000 kilometers. So the velocity is also coming to be around 3.08. So actual value is 3.17 kilometers per second, which if you remember when I showed you the live tracking, I told you to remember these values. So from where are these values coming? Now you know how to calculate these values when you are making your analysis. This formula which I have written just below that 2 pi r by time, it is the generalized formula for an elliptical orbit, because now what will happen is your every orbit is not circular in shape. So the velocity is mu is equivalent to 2 by r, where r will be the point where the satellite is placed at, that maybe it's at apogee or maybe it's at perigee. So r will be the actual point at which the satellite is placed, or the distance from the center of the earth to the satellite, and a is a semi-major axis. So in this case also, if I put that r is also equal to a, so it comes out to be mu by a, which you will find that is equivalent to what values you are getting for this case, right? For circular, it is we are using the linear formulas, but what happens is we need to actually use this formula, which is a generalized formula, where whatever be the satellite, whether it is circular or elliptical, this formula will always give you the correct answer. This is only for a specific case when you have a circular orbit. Is it clear? Yes or no? So the third law is very important because it helps us to calculate the altitude of your orbit as per the time period requirement, or time period as per the altitude. Basically, normally what you will calculate is the time period will be decided depending upon after how much time period you want to have another reading, and therefore it is the altitude which is calculated using the Kepler's third law and is very important for defining the orbital parameters. So this simply shows you very important thing is, what observation can you see with the animation drawn here? Are the speed of the satellite in both the orbits same? The one which is near to the earth is faster. Now why is it faster? You see, when you are near to the earth, there is a larger gravitational pull, and therefore to maintain your orbit, what is an energy that will balance the gravitational pull? It's the motion. and it's the velocity that will help you to have that energy to actually be able to overcome the gravitational pull. Okay, so always remember that the nearer is the orbit, the higher is the velocity, and therefore what is happening, this is because of the gravitational pull of the earth. Okay,
And 3 kilometers per second.
yeah, 3.17 or 3 point something, yeah, correct, crucial, it's correct, 3.17 kilometers per second. Geostationary orbit has a uniform velocity. Why does it have a uniform velocity? Because when I gave you the formula for velocity, that is mu equal to 2 by r minus 1 by a. So depending upon the distance of the satellite from the earth, the velocity will vary. Because r is varying, the velocity will vary. The second question is, justify geostationary satellite has a uniform velocity. How will you justify this point?
Ma'am,
Because
it is
it's
a
a
circular
circular
orbit.
orbit, correct? So the gravitational pull is uniform on any point on the orbit, and therefore to balance it, it has to require a same energy. Same energy means with the same velocity, it has to revolve around the earth to balance the gravitational pull of the earth, correct? Okay. Now the third question is, justify the shape of a geostationary orbit is circular. How do we say that? Although Kepler says that the orbit is elliptical in shape. Now circle is an
Hello.
ellipse. Yes. Yes, please
Oh,
speak. So circle is a special case of an ellipse with eccentricity equal to, correct Mohit, special case of an ellipse with of circle with the eccentricity equal to 0. Now geostationary satellite is defined as a natural resource. Geostationary satellite is said as a natural resource. Why? Because I have already written the answer. Everyone can use it, is not. Natural resource is something, yes, everyone is using it. It is just only one orbit that is existing, which because it has got a 0 degree of inclination, and it is aligned with the equatorial plane, and since it is only one such orbit, that is why it is called an orbit with a it is only one such orbit which has got a 0 degree inclination, aligned with an equatorial plane, and having a time period of 24 hours, and therefore it is called as a natural resource. Now, what is an inclination of a sun synchronous orbit? Uniform with respect to the line joining the center of the earth and the sun, but it is continuously changing so that it is able to maintain it, so that every day this orbital plane changing its inclination by 0.987 degrees per day, and it completes its one revolution, yes, 1 degree approximately per day. It is changing its inclination, so that now what is orbital perturbations? No, ma'am. Okay. So basically, when Kepler gave us this three laws, right, to define an orbit, define the time period, and actually define the shape of an orbit, he assumed Earth to be a perfect sphere, right? But what is an actual scenario? Everyone knows that Earth is not a perfect sphere, but it is oblate at the center and flat at the polar region. So it is like a oblate structure. Now what happens is your mass uniform if it is not a perfect sphere? No, the mass is not uniform. It has more density or more mass at the center as compared to the polar region. Now wherever there will be more mass, what will happen is you will have a larger gravitational pull, or there will be a gravity gradient existing. Now what is happening is, when I launch a satellite, because the question may come is, once I have launched it in the what I was talking about is this, when Kepler gave us these laws, he assumed it to be a perfect sphere, and as per this Kepler's law, it was assumed that all these bodies in the sky are orbiting at the in the uniform at sorry, not at a velocity, balancing these forces. And it was assumed that once you launch a satellite in an orbit, it should maintain its orbital path, but and should not lose it. But what was an actual scenario? The actual scenario was the satellite was actually leaving its orbital parameters and deflecting just because of the oblate nature of the earth. Oblate nature of the earth, there was a gravity gradient existing which was continuously actually deflecting the satellite from its orbit because the gravitational pull was changing. And this definitely what it will do is it will try to change the orbital parameters. What are the orbital parameters? The 6 parameters that help us to define the orbit are A, E, I, omega, and ran and m. Right? I told you in the when I was defining the parameters. Now what was happening was one of these parameter or more than one parameters were changing because of this oblate nature, and which was actually changing the position of the earth, because, and this is called as orbital perturbations, the variation in the orbital parameters because of the non-uniform mass distribution. Because earth is not a perfect sphere, there is a non-uniform mass distribution which is actually causing a change in the gravitational pull, and which will result in variation of the parameters, that is called as orbital perturbations. And we need to have a check on these orbital parameters continuously so that you are actually able to track these parameters. You are able to track these parameters and keep your satellite in the correct orbit. And there are other reasons for orbital perturbation, not only the non-uniform mass, the gravitational pull of the sun and the moon, the effect of storms in the sun also. These are certain parameters which actually change the gravitational pull and try to deflect the satellite from its predefined orbital parameters. This is called as orbital perturbation. Now, what are the effects of this orbital perturbation? The first, I told you, the first reason for orbital perturbation is non-uniform, non-spherical shape of the earth. Now, this non-spherical shape of the earth, the first thing that may happen is that there will be the change in two planes. One is called as sliding of the node, also called as regression of the nodes, and the other is called as the change of the orientation of line of apsides, that is called as regression of the rotation of the apsides. So the first two things that we'll be doing is, one is regression of the nodes and the other is rotation of the apsides, and then we will go to some more effects of this. Actually, the video is not, audio is not required. This is a simulation done in lab view. You just observe this. I'll just want to show you that this point right now you see it as intersection of this ascending node and the orbit with an equatorial plane. Just keep on observing this. After some time of rotation, what is happening to the orientation of this point of intersection? So what is this yellow line representing is your Earth's equator, and this red line is the line joining the center of the Earth with the center of the sun. That is the vernal equinox point. Now what is happening is, with the time, can you see the orientation shift? Now what is happening is, because of this is, there is a change in the reference point. This change in the reference point, now what is happening is, what are the parameters that are related with the vernal equinox? Ran, perfectly. So ran is what will change because of the change of this particular point. Or basically what do you see was your point. What was your ascending node? Ascending node is the point of intersection of your orbit with your equatorial plane. So the point of intersection was sliding, right? So that is called as regression. That is why this is called as regression, because the point is sliding. Now in this, there were two motions that will happen. Is one will be this regression is always in the direction opposite to the direction of, did you observe that the regression was opposite to the direction of motion, or do you want to see it again? Plan is changing because there is a shifting of a node that was visible. What direction was it shifting? Was it shifting in the direction of motion, or was it shifting in the direction opposite to the motion? Do you agree to this point na? Ye aapka direction of motion hai. This is moving towards east. The node is moving towards the west. Okay, it is d ohm by dt is equivalent to minus cos of I, where I is your angle of, I'm sorry, it's minus k, cos of I, where k is the proportionality constant. Okay, and the unit is in radians per second. Okay, now let's again analyze this particular equation. Now in prograde orbit, what are the values of I? I varies from 0 to 90. You remember what was the prograde orbit? It was an orbit where your inclination varies from 0 to 90. So when it is 0 to 90, what is happening is this cos of I will be positive or negative. It's a first quadrant. What will be the value of cos of I? Positive? Yes? Correct. Okay. Now when it is a retrograde orbit, what is the value of I? I is between, it is greater than 90. So what will be the value of cos of I? Cos of I will be second quadrant. Cos of I will be negative. So this term d omega by dt will become positive. That means the node will regress eastward, right? So in prograde orbit, the node moves westward. In retrograde orbit, the node moves eastward. In this, there is a very typical example that is you'll find, and a problem being asked in your books, papers is, suppose this is my ascending node, okay, and P is the time period that is defined for an orbit to move from an ascending node to an ascending node, right? And if I is your angle of inclination of the orbit, tell me how much will be the actual time it will take for the node, for the satellite to complete its one orbit. Is my question clear? I repeat, this is a very important question that comes in your as a proof is P, find out P, which is P is nothing but a time period to complete one revolution. One revolution is defined as from ascending node to the ascending node back. Can anyone tell me, will it be P or will it be simply, let me say, find T, let me say time period T. If this has P as a time period defined under ideal conditions, right? P is a period for ideal conditions, means there is no shifting of the nodes. P is for ideal condition when there is no shifting of the nodes. Can anyone tell me this period will remain, T will remain P, or will there be any change? By how much will it change? Can anyone tell me? Let me tell you that what is happening is once it is completing this node A would have shifted to a new point, or have assumed the direction of motion of the satellite like this. So there will be a regression, you know. Regression will be this node will shift to a new point A dash. So for it to complete its period, it has to actually come back to A dash. So the time period from moving A to A dash, because this node has shifted, is nothing but P already defined. But actual time period is once it completes its actual revolution back to point A. So we need to actually calculate how much time will it take to move from A dash to A. How much time will it take to move from A dash to A? That will actually define your total time period, where it will be P is equivalent to, sorry, T. T is equivalent to capital P plus small t. I want to know the value of small t. Yes, something related to the node, because it has to complete its 360 degrees, and but the node has actually shifted. So P is defined as from the node to the same node. Tell me how do I calculate this t? ये कितना पीछे जाएगा? क्या ये मैं angle find out कर सकती हूँ? Is it clear? Am I clear? So the total time required, this is an important formula, required to cover will be T equal to P plus cos of phi, depending upon whatever inclination. Can anyone tell me what will be the inclination to have no effect or no regression of nodes? Yes, what will be I, where I will not experience any regression of nodes? So polar orbits do not experience regression of nodes because they have cos of phi, sorry, the angle of inclination equal to 90 degrees. I will just like to repeat what is regression of nodes, because it's a little tough topic and it is important that you understand it nicely. Now, what is regression of nodes? See, I removed the negative sign by Kirti is asking me, why did I cancel this negative sign? Abhi negative sign kya represent kar raha hai? It is only representing the node has shifted back. But that also means that this is an additional time required. So time kitna require hoga? The angle into divided by the angular velocity. So will it have a negative sign or will it be a positive value? It's an additional time required, or is it reducing your time period? Tell me, Kirti. You agree with me? It will be a positive sign. That has a negative. This is only a representation that the point has shifted back, and this is an additional distance for which we need to calculate the time, or additional angular displacement for which we need to calculate the time. I'm repeating what is regression of nodes. We have seen that initially the ascending node may be having some fixed orientation, ye A point pe hai, and we define the time required for a satellite to move from ascending node to the ascending node is P. But what is happening is, with the time, there are so many Earth's oblateness results in some slipping of this node, which is called as regression of node opposite to the direction of motion of the satellite. Now, because of this, there is an angular displacement, but time required, as I told you, PA, irrespective of, it's not 360. Somebody wrote 360 in the chat. It is not 360. It is from the ascending node to the ascending node. I told you that it is from the definition of time period is from the ascending node to the ascending node. So, but the ascending node has shifted. But to calculate the total time, you need to complete the 360 degree. Now, to complete 360 degree, you are traversing some path in time t, but in that time, the node has actually regressed or shifted back in a direction opposite to the motion of the satellite. That we can calculate using our relation for regression of nodes given by d ohm. That is, since ascending node, what is a parameter we measured with the ascending node? It is your RAN. So the RAN is shifting or changing, and it is given by minus k cos of I. So in time p, this t dt will get here. Time is p. There will be some regression of nodes given by minus k cos I p. So this value is the additional distance that the satellite has to cover to complete its one time period. Now, one time period to complete it's given by, to calculate the time, it is distance by the velocity. Since it's an angular distance, the velocity is angular velocity. So the time additional required will be k cos of I p by n. I told you there is a special case where there will be no regression of node. That is when I is equal to 90, cos theta is equal to 0. So then T is equal to P, and that is a case for a polar orbits where the inclination is 90 and therefore they do not experience regression of nodes. There is something called as rotation of upsides. This is because your orbital plane, we have already seen an example of a sun synchronous orbit which is changing its inclination with the time so that it is always covering the same portion of the earth at the same sunlight, that is local time. What is happening is these orbital planes actually are changing their orientation. Now, because of this, there is the line joining the apogee and the perigee is also shifting. So that is called as rotation of apsides. What is the line joining your so this rotation of the plane is also called as, or represented through the rotation of apsides. So I'll just like to first show you this video and then we will discuss the way we discussed rotation of apsides. ये आप लाइंस को सिंपली ऑब्जर्व करिए. ये पहले जो स्टार्टिंग पॉइंट था, सी all the three orbits are aligned with this vernal equinox जो हम लोग का था पहला वो red line. Now slowly see what is happening is there is a change in orientation of each orbital planes. ये जो lines है आपका, ये जो center पे था, it is now shifting. Now this rotation of apsides, we could see that with the time again the planes are changing their orientation with respect to a point that, and because of which what happens is there is a change in argument of perigee. Well, how did we represent argument of perigee? The argument of perigee was represented by omega, small w. So it is given by the relation d omega by dt. So d omega by dt, that is the argument of perigee. Now because of the shifting of the line of apsides, what parameter changes is your argument of perigee, and it is given by the relation k, the constant of proportionality, 2 minus 2.5 sine square. It's sine square I. I'll just write it again. Sine square I. Okay. So sine square I. Can you tell me when will this value be positive, or for what values of I will it be positive? See, sine of 0, it is 0, it is positive. Sine of 90 is 1. See, sine of 90 is 1, it will become a negative value. So between 0 to 1, see, sine theta is positive in the first and the second quadrant, but for certain values, it will be positive, and for certain values, it will be negative depending upon this difference. Okay, perfect. They not only accept 90, it could be some 85 also, you can try. Now tell me, I'll tell you the right value after which it will be positive. Now tell me when it will be 0. Can anyone tell me when it will be 0? After that, it will be positive, right? Till that particular point, it will be positive, sorry. And after that point, it will become negative. Can anyone find out and tell me what is the value of I when this particular term will be 0? It is sine inverse of square root of 2 by 2.5. बराबर बोल रही हूँ? Yes. Tell me what is this value? This term is 0. So either this is 0 or this. Perfect, Kirti. It is 63.545. Now do you remember? Molniya orbit. Which orbit had this orientation? Which orbit? Perfect question. It is 63.43. This was an inclination of Molniya orbit. Now, do you know the reason why Molniya orbit was? I'm sorry, the spelling is wrong. Now, do you know the reason why Molniya orbit was made with an inclination of 63.43? Because at that orientation, your rotation of apsides is 0. These are important questions that you need to remember or justify why 63.43 is chosen for Molniya orbit. The answer is because at that inclination, your rotation of apsides is 0, right? Now, the same question which I gave you in the last example, normally that question comes is as a combination that this may have either angle is say given to be some 90 degree, and you could be asked what is your additional time required to complete, because in both the cases what is happening is your orientation with respect to the ascending node is changing, right? Whether I say regression of nodes or rotation of apside, हमारा reference point क्या था? Ascending node. वही shift हो रहा है, तो what we need to do is calculate an additional time required to cover that particular distance. So sometimes you can be asked as a combination giving a certain value of I where both are existing, that is regression of nodes and rotation of apsides, and sometimes they may give either I equal to 90 or I equal to 63.43 and ask you to calculate the other. Earth is not a perfect circle even in the equatorial. Equatorial plane is also not perfectly circular. It is oblate. It has got an eccentricity of 10 to power of -5. Very small, but still it is not perfect sphere, right? Are you getting my point? This is an important point to remember. This equatorial plane is not a perfect sphere and has got an eccentricity of 10 to power of -5. Now, what does this mean? There will be a eccentricity अगर नहीं है perfect sphere, तो mass will have a gravity. Mass is not uniformly distributed. It will have a gravity. Okay, so gravity gradient. Now, gravity gradient means what? It will have an additional gravitational pull at these points or points coinciding with these particular points where you have a higher mass, which is actually, it will have a higher mass, and therefore your satellites will experience additional pull at these points. Now, these additional pulls, how we can overcome these gravitational pulls or gravity gradient that is existing? Definitely, it will try to change the orbital parameters because it is pulling the satellite towards it and moving it away from its orbit, and therefore we always need to have keep a check on the orbital parameters and keep the satellite. Now, what happens is after the satellite life is over, right? Satellite life is over. Can you tell me, is there any force or any control that we have on the satellite? Do we have? Yes or no? It's the
No.
lifetime. No, perfectly. We don't have any control over the satellite. So after that, what happens is you have lost a communication contact with the satellite. You cannot control it because it does not have the power to actually bring it back to the orbit. So what happens is after the lifetime of the satellite, these gravitational pulls try to pull the satellites towards them, and these are aligned 180 degree. They are displace point aligned with 75 degrees east and 105 degrees west. So after the lifetime is over, these points of gravity, higher gravity gradient, keep on pulling the satellites towards them, and they are also called as satellite graveyards. They are also called as satellite graveyards because after the death, or basically after the lifetime of the satellites, all the satellites drift to these points, that is 75 degrees east and 105 degrees west, after their lifetime is over, and therefore they are called as satellites graveyard. The after basically what happens is after the lifetime is over, what they may have some fuel. With that fuel, they are given an additional push out of the orbit so that they don't become debris or the waste and trying to interfere with the other satellites, new satellites that may be there in the new satellites that may be there in the space. Now what happens is sun orientation of sun with respect to the sun uniform or non-uniform? Can anyone tell me? Sun or earth ka orientation, is it always uniform or non-uniform? Sometimes we are
Non-uniform.
near, non-uniform. Sometimes you are near to the sun, and sometimes you are away from the sun. All of us know the earth axis is tilted, and we are near to the sun, what is happening is we experience summer, and once it is away, we experience a, right, you know, na, reasons for season. This is how the earth's orbital axis of rotation is with respect to the sun. So once we are bending, this is a point of summer, and once, and I mean, say in northern hemisphere, southern hemisphere is experiencing winter, and when it is a case like this, northern hemisphere is experiencing a winter, and southern hemisphere is experiencing a summer, right? So what is happening is when you are near to the sun, what is happening is there is more solar radiations, right? So radiations and the impact of the radiations on the orbit is that the solar radiations, it will sometimes reduce the eccentricity, or basically it will try to shrink your orbit because the radiations are higher, and sometimes it will try to expand. So it is like for 6 months, we have eccentricity is converging or reducing, and for 6 months, eccentricity is increasing, right, depending upon the season. So eccentricity keeps on varying, and because of which, as you can see, which is the parameter, orbital parameter, that will change because of the change in, one is eccentricity itself, AEI, and the second is your A. A will also change because with the eccentricity, the shape is changing, the length of the apsides is changing, right? So that is called as solar radiation impact on eccentricity, and it is clearly shown in the diagrams that there is a atmospheric drag, right? What is an atmospheric drag is, this is my satellite, okay, this is my satellite. Now, when you are near to the earth, this is basically the light curve that you see is the earth's atmosphere, and beyond that the impact of earth's atmosphere is reducing because the density of the air is reducing. You are, once you cross this, the impact of the earth's atmosphere is reducing. But as soon as the satellite enters this or near perigee, you can see that there is lot of resistance. This atmosphere will actually exert lot of resistance on the, it will exert lot of resistance on the satellite. So what will happen is the impact of resistance is velocity reduces, right? Do you agree to this? As velocity reduces, will it have the energy to reach to the same point? No, because the energy is actually defining at to what altitude your satellite will be able to go. So the altitude to which your satellite will go will reduce. Now, what is an impact of this if the altitude will reduce? What is reducing? Altitude is reducing. What is happening is, which parameter is reducing? change hui. Correct. Kirti, A will change, right? Your semi-major axis will keep on changing. Your one of the orbital parameter that is changing is straightly is because of your height, as you say, it is A that will change. And what we have to do is every time there is a reduction in the velocity, we need to provide an additional thrust so that if we don't keep it, attend to this particular problem, slowly the orbit will reduce and satellite will definitely fall back and will not be able to control it. So every time there is a reduction in velocity, we need to give it a thrust so that it maintain its orbit and this impact of atmospheric drag can be reduced.
मिस पर वो वेलोसिटी क्यों चेंज होगा मतलब वो एक ऑर्बिट से?
अगर तुम एक जा रहे हो रास्ते पे, स्पीड ब्रेकर आता है तो क्या होता है, तुम्हारी वेलोसिटी कम होती है या नहीं?
हाँ मिस।
स्पीड ब्रेकर है तो अभी ये क्या है, आप you are moving from this particular point and this is like resistance is nothing but it's like acting like a speed breaker. Resistance क्या करेगा, it will move the satellite के ऊपर act करेगा to reduce its velocity. ये जो एटमॉस्फेयर है it is like a resistance to reduce, क्योंकि उसको पार करने के लिए it requires some energy. तो एनर्जी लॉस होगा, right? So energy loss होगा तो will it be able to maintain the same velocity? No.
No
And
miss।
if velocity is reducing तो वो height पहुंच पाएगा नहीं, क्योंकि एनर्जी नहीं है, and therefore there will be a reduction in the height. So LEO orbits face this major problem. GEO don't face this problem because they are already at a very high altitude, right?